Hello, thanks for hanging out so late. I guess we're going to go from what I heard, layer 9 all the way to layer 1 with this talk. So it's going to be an interesting transition. But basically, this work is supported by the NSF and Rome laboratories, and it has to do with designing and implementing high-speed programmable hardware. Right now, we're working on 10 gigabit per second. So let me give you a brief history. So I was a DARPA PI in the Active Networks program, which was a program that was designed to improve the programmability of networks and allow the networks to adapt to new protocols, new flow control mechanisms, ad hoc monitoring sort of applications. There were two kinds of active networks, more sort of discrete, where it was actually the adaptability was performed through management operations that are separate from the data flow. And then there was an integrated version where instead the packets themselves brought the updates to the network in sort of like a very sort of fine-grained and dynamic way. So the broad scope of this research program did not really result in a wide industry adoption, although there has been very, very good research that came out of this, very fundamental research in how to design safe programming languages for network sort of applications, hardware prototypes, and so forth. So meta networks, which basically I started after that, it basically has the same goal, but we're trying to be more pragmatic, and we try to do a bottom-up approach where we want to achieve the programmability, but we want to not be invasive, not having to change the routers and the network components in the network, and also we want to be application-driven rather than design-driven. And lately, we've been actually revisiting the computational model for specific applications. In our case, is a network security application in the IDS, IPS space. And this talk is going to be about exactly this last bullet. The design guidelines that we have sort of in mind are basically to be open source so that we can reuse the open source have the open source model where we think it's open source in general provide more flexible, more robust sort of software sort of applications. And so in order to do this, we directly support currently the SNOR signatures, and also we abstract our hardware system from as a PCI card that looks like a network interface card. So you can put it in any PC or Intel-based machine, and it appears to be a network interface card. And the basic, also we want to retain high degree of programmability and line speed, and sort of we'll get into more of the programmability aspect of the hardware. So what it looks like is basically, as I said, a PCI card, and on the left side of the of this slide, you see there is basically a layer 1 forwarding mechanism. That's why I'm talking about layer 1. This essentially acts like a tap. It basically has two ports, and the packets just go through this layer 1 system completely transparently at line speed, and it doesn't care what protocol it is. Protocol is being transmitted. It just line speed with the clock is basically forwarding the packet back and forth. As this is happening, some packets are also copied to our own version of a network processor, and the rest of the talk is really going to be about this piece of the whole architecture. This network processor has some memory to which it can keep stateful sort of information about the packets. And the result of the matching that happens in here, you can have packets being copied through the PCI card to the host as if they were coming from a regular network interface card. So it's like if you had a network interface card in promiscuous mode, you will see packets coming to the host, and or can be blocked. So there's a signal coming back here to the layer 1, which basically gates the forwarding of the packets. So in essence, this becomes a sort of like an IDS accelerator or an IPS system. So I'm going to be talking about what's in here. And I'm going to start from a sort of high-level view of what's called the Flynn computer taxonomy, which basically tells you all possible ways that you can do computation. Flynn came up with this taxonomy, as I'm going to direct you toward what's currently being done today, what we're doing different. So basically, this is the simplest type of taxonomy where you have just one data flow and an instruction flow. And the process combines the data flow and the instruction flow to come out with the computation. The parallel version of that is called MIMD, multiple instruction, multiple data, which takes multiple data flows and multiple instruction flows and has several processors that compute in parallel on these multiple flows. This is basically what is being used today in most processors, both superscalar processors like your Pentiums and your processors in your modern computers, and network processors. So this model applies well to network processors because what network processors do is exploit what is called the packet level parallelism. So they see each packet as an independent event and assign each packet to sort of one of these processors, and they have multiple threads all working concurrently to process each packet concurrently. And so the overall throughput of the processor increases because of this parallelism. There is two other not so well-known types of computational models. There is the single structure multiple data, or SIMD, which is basically having all the processors getting the same instruction, but each working on a different data stream. This is the kind of processors that will be used, for example, for image processing applications where you have large screen and each processor gets a portion of the screen, and all processors are given the same instruction to do, say, interpolate. And all the processors each takes a region of the screen to do the processing. So this is used in some special purpose sort of processing applications today, but it's not as popular as listed. And then there is this fourth one, which is the multiple instruction single data, and that's actually the one that we feel is the best suited architecture for security applications, network security applications. So I've got to hurry. So this is the instantiation of that architecture where you have a data stream that is broadcast inside an FPGA, and basically there's a number of small processors inside this FPGA, which each implements a rule. So basically, if you're trying to look for about 1,500 attacks, each one of these will be responsible for looking for that specific attack. Then there is a reduction network which takes the result of all these processors and combines the result, goes through a stateful analysis stage, and then back out to the host processor. And basically the interface between this processor and the host is basically the PCI interface. And this can be done basically synchronously with the receive clock of the data stream. So line speed. So an interesting problem is, given an FPGA, you have, say, a large number of snort rules. How do you make best use of your logic inside the FPGA to be able to fit as many snort rules as you can inside a given amount of logic? And one of the techniques we use is basically share comparison logic among multiple rules. So here I have, I'm trying to look for a string called match this into the payload. And then I have another string that says catch this one. There is an overlap between these two strings. And so we have basically a compilation technique which allows you to encode these two strings by reusing some of the comparison logic, in this case TC, HT, and HI. Then the actual FPGA synthesis tool will take this and further optimize to achieve further optimizations. So this basically shows you what happens if you grow the number of rules. So here's the number of rules, and here's how many components you have in the FPGA to implement them. And the growth is sublinear. So because of this technique, basically, if you increase the number of rules, the number of components is not going to increase linearly. What increases is the number of connections within the FPGA. So basically, you're going to have a highly connected system, but with fewer logic, which is really what you want. Okay, so one of the problems at 10 gigabit per second is that you're now approaching a bandwidth in which the bandwidth that you're monitoring is approximately 100 times the bandwidth that you have to be able to report information to the host. So the nice thing about being at wire speed is that flooding, if you flood the line, you cannot compromise the blocking capability. So this is a good, an essential characteristic. However, obviously, by flooding, you can also reduce the efficacy of the reporting mechanism, because the host now is going to be overwhelmed with reports if you're getting flooded with malicious packets, so to speak, or packets that are deemed to be bad. So, the problem is that you want to find the needle in a haystack when you have so much bandwidth. And three techniques that we're looking at is stateful, which we already do, then what I call intelligent monitoring and application level programmability. And I'm just going to be very quick about this because I don't have time, but I'm just going to outline very briefly these last two techniques. So intelligent monitoring is basically assigning a leaky bucket to each rule. So you have, say, 1,500 rules in you're trying to monitor that indicate 1,500 different types of attacks or 1,500 types of things that you're looking for. And each leaky bucket measures basically the arrival rate of the matches of that specific rule. Then what you do, you sum all the outputs of those leaky buckets and compare it to a general threshold that says this is the amount of reporting bandwidth that I'm willing to accept on this specific application. And then if you exceed that threshold, what you do, you switch the modality on some of the rules. Instead of reporting the packets, now you start reporting the occurrences of the matches. And so you basically switch some of the rules off, the ones that are causing the most bandwidth, reporting bandwidth use, and therefore you leave those rules that are useful to find very specific detailed information in place, but you switch off the ones that are actually causing you to lose bandwidth. We haven't implemented that, but we're looking for feedback to see whether that seems like to be a good idea. The other sort of approach is that when you're at 10 gigabit per second, you may want to be very specific about what you're looking for. And in fact, it may be that a snort rule may not be enough to really be able to specify what you're looking for. In fact, it could be a very complex type of inspection and monitoring sort of algorithm that somebody may come up with that may want to offload most of the computation in the processor itself at wire speed. And so what we want to do is basically allow users to instantiate application-specific modules within the processor that can take the wire speed data, do processing, and then reuse some of the common functionality in the processors, but basically allow users to be very specific about what they want to do near the wire, and therefore reduce the amount of bandwidth that is necessary to report this information. One of the nice things about this computational model that we're using and the use of FPGAs is that this is an active networks idea. I mean, this is not new. However, active networks was mostly based on the idea of using network processors to do this. And network processors have the problem that it's very hard to predict, once you add a user thread inside a network processor, what is that processor going to do in an operational environment. You don't have the abilities or the tools today to be able to predict that. With this paradigm, you actually can encode some user-defined applications in the FPGA, and because the mapping is static, it's done through the logic synthesis, you will be able to predict before you even instantiate the design in a network that it meets the timing requirements. If it meets the timing requirements during the logic synthesis, you're guaranteed that it's not going to sort of affect other functions that are within the same processor. So that's a nice sort of property that allows you to have a much more higher level of confidence of basically in the adaptability of your system. So this is a summary, is that doing this bottom-up design is promising. So in bringing line speed acceleration, the very low latency seems to be a very good feature because it allows this to be inserted in a network without really limiting the performance. It allows you to basically be completely transparent. And the very surprising fact about this research that the 10 gigabit Ethernet board is not 10 times more expensive than the 1 gigabit in terms of computational resources. The scalability of this architecture is much, much better than I expected when I started this. So it's a very good sort of thing that came out. In fact, we're building some 10 gigabit boards today, even though we have limited funds. But since the fabrication and the components are pretty cheap, we have the resources to do it. Basically, one of the big nut to crack in this research is the composability issue. So once you have people developing different modules that you can instantiate in these processors, be a network processor based or FPGA based, the real hard part that I'm interested in, and I don't really have an answer yet, is how to support the composability of different modules that may interact with each other. So you don't have to reinvent the wheel every time, but you can reuse each other's sort of code and sort of compose system, much like it happens in Unix. You have a very, very nice composability model which allows you to share different sort of applications and it really increases productivity and the scalability of the system. Anyway, I didn't have much time to go into the details, but please contact me if you want more information. If you want to discuss this, give me feedback. If you have ideas of what you want to do with this in terms of your specific applications.
Thank you. We have some time for maybe a few questions if there are any. No? Susan, thank you.